Ready? Hello, welcome to our digital and technological solution to behavior-based safety in the construction workspace. It's brought to you by Robert Lester, Alexander Cito, and Brian Savage. And we'd like to thank Sterlite and MIT for giving us this awesome experience. So the problem presented to us was that construction sites tend to be a lot more dangerous than other industries. Both of these figures are from the spec, and we see that construction has a higher fatality rate than all industries over an average. And then we also see the injury rate itself is statistically significantly more than all industries as a whole. And so the solution proposed to us was behavior-based safety, which is the concept of promoting the elimination of unsafe behaviors in order to prevent them from evolving into injuries or fatalities. And so an unsafe act may be like not wearing protective equipment or being distracted on the job, while an unsafe condition might be not cleaning up after yourself or it being windy out. And so the idea is to stop this immediately when we see it and provide feedback to the employees at the workspace and then correct it. And so we've seen success in this in practice because one, there's a positive correlation found between unsafe behavior and injury rate. And then when we do implement BBS, it tries to eliminate these unsafe behaviors, and we see that injury rates and severity rates go down as in practice here.
So our solution to this challenge was to develop a cost-competitive and scalable safety management system solution based on behavior, as well as provide an advanced analysis to supervisors in order to, in the future, create predictive and leading indicators rather than reacting to lagging indicators. So the summary of this was to develop a web and mobile application which works threefold. It connects employees and supervisors and observers to provide like immediate response to unsafe conditions and accident reports, and also use this to log simple report data as well as to leverage into machine learning solutions in the future, as well as promote memory of these incidents for future follow-ups with supervisors and interviewers in order to construct a more in-depth analysis of behavioral patterns. And so we've seen in our studies previous proposals of architectures of similar solutions. However, we have thought through the potential AI and machine learning applications of the data that we can collect and exactly how we want to go about collecting that data. So I'll be quick about this, but this is our base implementation of the architecture of our application. So we're going to have the ability for observers, supervisors, or employees to file a report and submit a report form about an unsafe condition or action, which is then sent to a supervisor who can send a response saying whether to stop working or not. And then it will respond with prompts based on machine learning intelligence based on past fixes in order to provide rapid solutions for these problems, and they can communicate until it's resolved, and then they schedule a follow-up interview in order to go into further detail to examine these behavioral patterns.
So the main structure that we have is our alert system. The alert system allows for supervisors to know real-time analytics on the job site, and it also allows for workers to get real-time feedback on previous accidents that have occurred at that work site and that are repeat occurring. The main aspect of the alert system of how it works is we run clustering on the previous form entries that have been submitted to the database. So it looks at the overlaps in forms and seeing what solutions have repeat occurrences of being. It looks at the database, it finds which papers are similar, and then from that, it determines which solutions will be most effective for this current issue. This would be an example of an accident report. What it does is we have categorical fields for each entry. Through using categorical fields, we can find the frequencies of injuries occurring, their sources of injuries, and the conditions that led to them. This would be an example schematic of an alert. This is the example implementation that we have. And so with this is design, but the actual implementation of how it's going to be designed is these three main models. The three main models are a low-cost implementation, a mid-cost implementation.
Time is up. Please wrap up. Any final thoughts? Thank you.
No, of course. So each implementation builds upon each other. The linear regression just looks for trends in the data. The fuzzy model basically looks for the most effective solutions to problems and what has shown previous success. And finally, the computer vision basically divides images into subset images, identifies where workers are in those images, and then from there, using machine learning, it classifies, in this example, there's 4 conditions: safe, not safe, hard hat, no hard hat. And from there, we can run a logging system and track in real time what a job site, the safety of a job site. This is just a model of how the actual fuzzy logic would be implemented to make these predictions. And those are the sources of our information. Thank you.
Great, thank you. And let's have 5 minutes of question and answer.
Of course, whatever you guys need.
See, one of the key challenges that our problem has is about this being a linear asset and remote asset.
Mhm.
Things will happen at very difficult terrains, etc.
Mhm.
So unless you have the data, these models don't run, right? So have you thought about how do you collect the data? How do you simplify that collection of the data to run the models?
So one of the really nice parts about using computer vision to make these predictions is that it's a supervisor node that acts completely autonomously of human intervention. Through identifying where workers are inside the image and also classifying their current safety status, we can look at trends and look at the real-time log at a job site for the level of safety and if a supervisor needs to make further mitigations to improve safety or what conditions are leading to more unsafe conditions. Do you guys want to?
Well, also in addition, the data can be supplemented with other construction data safety reports from like other sites from the same company as well. We used, in order to show this slide, we use data. This is real data. This is OSHA reports, actually incident reports, but our incident reports would be slightly different just to capture a little more of the whole entire situation. But here we see that we can supplement with previous construction data.
That allows for like future predictive analytics for taking preventative measures, which, yeah.
Yeah, all this data will help you to refine your model or perfect your model. But you still need to have the real-time observations, which when you are feeding it to the model, then it will generate whether things are going right or not. So still you need to capture real-time at the site certain data, capture certain observations, which are what fed into the model. So
Well,
how do you get that?
the purpose of developing a mobile application is we're assuming at least some degree of accessibility of workers to some sort of smartphone. So we're assuming that at least one person on the construction site might be able to have a smartphone, which will in turn allow them to communicate with the supervisor real time who gets these alerts in order to come up with an immediate solution. And while that data is being given to the supervisor, it's also being logged for future statistical analysis for leading indicators.
And so the idea of the real-time suggestions is that from all the previous reports we have, we cluster them together, which basically means group them together. And so when we get a new report, we go into our database, we find the cluster it corresponds to or the group it corresponds to, and we're going to look at the top. We record all the effective solutions from before, and then we output them. We out the top 5 most frequent effective solutions corresponding to that cluster.
See, you introduced a layer called observer at the site, right? At every site there is a supervisor, there is a worker, and then there is a observer. So can you tell me the role of the observer and how do you see that person doing and what he's doing? Is he an additional layer that needs to be added according to your model?
We see that as hypothetically, that would be an ideal case to be able to have an observer on a work site dedicated to maintaining safety and communicating with supervisors to, maintain safe conditions to prevent unsafe behavior, and also that creates a environment of safety. And ideally that would be the case. However, the accessibility of the mobile application would allow an employee, like a construction site worker as well, to communicate with the supervisor regardless.
The last thing is, so when we're using, for the high cost implementation using computer vision, the nice part is we can train our models completely on, it's independent of certain working conditions. Like someone wearing a hard hat is independent of location. That's just something we could train the data set upon, or the model upon. That also allows, since it's completely autonomous detection and logging into our database, it requires no human intervention to monitor these things. It's just security feeds, looking at different LiDAR detectors on how machines are operating, their stress loads, their different, like the supports under them. And that allows for completely autonomous intervention and recommendations in real time to workers without a human either logging a report or categorizing the recommendations or proposing solutions that would be most helpful.
And so this computer vision can act itself as an observer node in our system, such that it can just be there and continuously seeing if it needs to report an unsafe condition or unsafe act.
Okay, thank you. Thank you.
Thank you.
Thank you.
All right, great. Thank you. Thank you for your presentation, and have a good rest of your day.
So
Thank you, you too.